Okay, so today we will enter to the last part of the course. We already saw the first part that was about Lefschetz theorems, about the topology of algebraic varieties. The second part was about the L2 Hodge theory, that it's all Hodge results. And the third part that I finished the last class is about Serre's theorems, right? About the coherence of, I mean the coherent shifts on projective varieties. Okay, so this last part will be about mainly about Griffith's theorems, and I plan to prove Griffith's theorem on the hypercohomology of hypersurfaces. I will give you an explicit basis of the Hodge filtration of any hypersurface, if you smooth hypersurface, if you know the equation of the hypersurface. And if we have time, after that I can tell you a little bit about variations of Hodge structures. Okay, this is also part of the work developed by Griffiths and his collaborators. Okay, so in order to enter to this part, I have to spend one class talking about hypercohomology. This is just continuing in the spirit of what I already did in the class of chief cohomology. So this is for topological spaces. Okay, so definition. So let X be a topological space. And Fd be a complex of shifts of abelian groups. Okay, so we define the hypercohomology groups. So they will be just the derived functors, the derived groups of the global sections functor. So it's just by definition this. Okay, this so in particular. If f dot is such that f1 and f2 and so on, they are all 0, then the hypercohomology is just the chief cohomology. Of f0. Okay. Whenever I'm talking about a complex in this class, it will be a left-bounded complex. Okay, it will start from 0, f1, f2, and so on. Okay, so this is a generalization of the chief cohomology for complexes of chiefs. Right? Okay, so first proposition that is trivial from what we already did in the class of derived functors. The following. So let X be a topological space. Dot D be a complex of chiefs. Okay, so first of all, so if FD is a resolution of some chief F, then so we know that the hypercohomology will be exactly the chief cohomology of F, right? Because I mean this resolution is exactly the same as giving a quasi-isomorphism between the complex that has only F and O0 and this other complex, right? So the hypercohomology of both complexes will be the same, and by what I already noted before, the hypercohomology of this complex is exactly the chief cohomology of F, right? So if this complex is gamma cyclic, then so again, but by what we saw in the class of derived functors, we saw that whenever we have a complex that it's gamma cyclic, we can compute its derived objects as just applying taking the cohomology of the functor applied to the complex, right? So it will be just the cohomology of global sections of the complex, right? In particular, whenever you have an acyclic resolution of a sheaf, you will get the isomorphism between the chief cohomology and the cohomology of global sections, right? And it's connected by the hypercohomology. Three. Whenever you have a quasi-isomorphism of complexes of chiefs, you will have an isomorphism of hypercohomology groups, right? Okay, 4. So if you have a short exact sequence of complexes of sheaves of abelian groups, we have an induced long exact sequence in hypercohomology. Okay, this all these propositions, we already proved them in a more general context of derived functors. Okay. 5, well, this is the zero group. Hypercohomology groups corresponds to the global sections of the kernel of the first map. Okay, so now I will explain how do you compute these hypercohomology groups in the same spirit that as we did with the chief cohomology, that we compute them, I mean, in a kind of explicit way. When we were using the check cohomology groups, we can do something similar in order to compute these hypercohomology groups. Okay, so definition. So let X be a topological space, U an open covering of X, and F be a complex of sheets. So we define the hypercohomology groups relative to U in the following way. So we define it, I mean, we write them like this, we denote them like this, and it's by definition the cohomology of the following complex L and big D, where Lk is the group defined as the direct sum of the CQ of the check cochains with coefficients in Fp, right? And D, the differential operator, is given by the following formula. So it will be, whenever you restrict D to CQ UFP, it is exactly the differential of the complex plus minus 1 to the P delta, where this is the check differential operator, right? This is the differential of the complex, and this is check. Okay, so it will go from CQ UFP to CQ UFP plus 1 plus CQ plus CQ plus 1 UFP, right? And it's elementary to check that this is a complex, okay? Okay. So the proposition is the following. Proposition. So let X be a topological space, U be an open covering, then first part is if this is a short exact sequence of complexes of shifts, and it satisfies the following property, that the first cohomology group of all the FP are 0 over all the intersections of the open sets in the covering. Then there exists a long exact sequence in hypercohomology with relative to U. Second part is the analogous theorem as to Leray's theorem. Second part, if it's a complex of shifts such that U is a good covering in the sense of Leray's theorem, for every FP, then the hypercohomology is exactly the hypercohomology relative to U. Okay, so clear? No questions? So the proof. Okay, in the first part, so the hypothesis implies that we have a short exact sequence of complexes here. So we have here it's exact for every P. Right, and so the induced sequence in the direct sums will be also exact, right? It's also exact and induce a short exact sequence of complexes, right? Okay, so this is the proof of the first part of the proposition. And the second part, that is analogous to Leray's theorem. It's as follows. So by hypothesis, the double complex given by the check resolution so we have here F and we have here the check resolution, so it will be a double complex like this. We know that it is a resolution for every P, and by hypothesis it is gamma cyclic. This is the hypothesis. So the induced quasi-isomorphism on the to the complex, to the simple complex associated, right? So we have here, we have a quasi-isomorphism with this other complex. And this complex is also gamma cyclic, right? So the hypercohomology groups, they will be the same. But since this other complex is gamma cyclic, we know that the hypercohomology is exactly the cohomology of global sections. And this is isomorphic to the cohomology of global sections of this. this is exactly the hypercohomology relative to U. Clear? Okay, so whenever we have a good covering for all these shifts, for instance, whenever we are in the algebraic context or in the analytic context, and we have complexes of shifts that are coherent or quasi-coherent, and U is a fine covering, we can compute all the hypercohomology groups in terms of an explicit covering, and this computation is explicit, right? With this check resolution and this simple complex associated to the double complex. Okay. Okay, so again, you can define some hypercohomology groups relative to, I mean, whenever you have a refinement of an open covering, you can define a map, a natural map, from the hypercohomology relative to U to the hypercohomology relative to the refinement. And you can take the direct limit, and you will have that this isomorphism will be also true, but without restrictions. I mean, you don't need to take any restriction on the covering effect. Okay. I won't prove this. Okay, so now I plan to talk to you a little bit about spectral sequence. But I won't give you the whole theory of spectral sequences. I just want to look at a very particular example. That is the example that we will be interested in. That is the example of the spectral sequence associated to the naive filtration of the hypercohomology group of some complex. Okay, so I will just give you the definitions in this context. I do this because I think that it's easier to understand it in this context, and later you can read it in the general situation, and you will have the intuition of why you define all these things. Okay. Okay, so definition. So let X be a topological space. F be a complex of shifts over X, and U be a good covering in the sense for the complex in the sense of Leray. Okay, so we define the naive filtration. complex L dot D in the following way. So Fr of Lk is by definition the following group. Okay, so it's the same direct sum, but you are starting from P equal to R, right? So the first part of this direct sum is you forget about it. Okay. So this is a filtration. This is a decreasing filtration. And satisfies that D of the filtration is contained in the same level of the filtration, right? Right? And so the pair, in other words, we have a filtration of the complex. So we denote it like this. LF is a filtered complex. Okay, and so we have since we have a filtration on the complex, this induces a filtration on the cohomology of the complex, right? On every hypercohomology group. Fr of the hypercohomology group will be exactly so the image of the cohomology of Fr LD inside the cohomology of L dot D. And this is exactly the same thing as the image of the hypercohomology of X relative to the truncated complex inside the hypercohomology, right? Where the truncated complex. Okay, it's not the translated complex. It's not shifted. It starts with a lot of zeros. You replace all the previous part of the complex by zeros. Okay, so these hypercohomology groups, I mean, the big advantage that you have with respect to the chief cohomology groups is that they have this natural filtration inside them, right? This is the most natural filtration that you can produce inside this hypercohomology group, right? And so something that we would like to have is the following. So when does this quotient, right, the f, let's say fp, we would like to have something like this, right? To get the cohomology of the chief FP. This is something that, well, that seems like natural to happen, but it's not always true. And the way to understand how does these two groups relate is via the theory of spectral sequences. Okay. So now I will introduce to you the spectral sequences associated to the naive filtration of the hypercohomology groups of a complex, and we will try to understand when does this happen. Okay. And you will see that, well, after we spend some classes talking about the relation of the hypercohomology group and the Rham cohomology, you will see that this is in such a way explaining the relationship between the Rham cohomology and the Dolbeault cohomology groups, right? And it's giving like a kind of Hodge decomposition, but it's not exactly the Hodge decomposition. Is something weaker than that. Okay. Okay. So definition. We'll do it here. For every well, again, here X topological space, F complex sheets, and U a good covering. Okay. For every P, Q, and R, we define the following groups. So the first one is Z, P, Q, R. It is defined the following way. So it is the omegas in Fp of Lp plus Q, such that d omega is in Fp plus R, Lp plus Q plus 1, right? So you have to remember here what is the definition of L. Okay, so Lp plus Q is a sum of so maybe I will draw Lp plus Q is what? So you have here F0, F1, F2, and so on, right? And here you will have C, P plus Q, U of F0. Here you have C, P plus Q minus 1, U of F1. Maybe I should do it in this other direction. Here you have F0, F1, F2, 2, and so on. Right, and right until here you have C0, right? And you take the direct sum of these abelian groups, and whenever you are taking the filtration, you're removing some part of this, right? You're starting from p bigger or equal than some point, some p, right? So here you're starting from p equal to 0, p equal to 1, and up to p plus q. So you're removing this part, right? You're forgetting about all this row. Okay? That's the filtration. You're forgetting these parts. And so whenever you're taking an element here, you're taking an element that you can think of it as an element of this sum, such that it is 0 from the beginning up to the row p minus 1, right? So it has a lot of zeros, 0, 0, 0, 0, up to cq of fp. And these other guys are non-zero. And the d of this sum of elements, the d will be 0 in more parts, in more rows, in p plus r rows, right? So it won't just be 0 up to the row p minus 1. The d will also cancel up to the row p plus r minus 1, right? This is what this group, I mean, how you have to imagine the elements of this group. Okay, so we define this C PQR. We define B PQR as C P plus 1 Q minus 1 R minus 1 plus D of Z P minus R plus 1 Q plus R minus 2 R minus 1, and this is contained inside Z P Q R. Okay, so we have to check that this is in fact contained in that, right? So you take here an element that belongs to Z P Q P plus 1 Q minus 1 or R minus 1. So the first P plus 1 elements are 0, right? And so obviously the first P elements will be also 0, right? So, and the D of this guy will belong to Fp plus 1 plus R minus 1 to, so it will belong to Fp plus R of Lp plus Q plus 1, right? So this relation is exactly the same. And so obviously this is contained inside this, right? And in order to check that the D of this thing is contained in CPQR, obviously this second condition is not important because whenever you apply D 2 times, it will vanish. So this condition will be trivially satisfied. So the only thing that you have to check is that the D of an element here belongs to Fp of Lp plus Q, right? And by definition of this group, the D of an element here will belong to Fp minus R plus 1 plus R minus 1, that is Fp of the sum of this thing plus 1, and that is P plus Q, right? So it's just by definition. So we have this subgroup of the CPQR, and we define the EPQ groups, EPQR, as the quotient. Okay, so since the D of Z EPQR is contained in the ZP plus R Q minus R plus 1 R, and also the D of B PQR is contained in the B P plus R Q minus R plus 1 R. We have an induced morphism dr, that is by definition induced by D, that goes from EPQR to EP plus R Q minus R plus 1 R. Okay, and makes EPQR dr a complex, right? And this is obvious just because of the big D being defining a complex, right? Okay, so this is well, this complex is called the spectral sequence. So this is called the spectral sequence associated to the naive filtration of L. Okay, so let's compute some of these groups appearing in this spectral sequence. So, so the first one to compute is EPQ0, right? So what is EPQ0? So EPQ0 is ZPQ0 over BPQ0. This is exactly what? So when we look at ZPQ0, we will get here the elements of the filtration such that D of this element is again in the same filtration, but that's always true, right? So this second condition is saying nothing, right? So it's just FP of LP plus Q, right? And what will be BPQ0? So BPQ0 will be CP plus 1 Q minus 1 minus 1 here. So again, this second relation will be saying nothing, but it's saying that this ZP plus 1 is saying that we are in the filtration P plus 1 of LP plus Q, right? And this other group, the D of Z P plus 1 Q minus 2 minus 1, this is contained in this first group, in the case when we're taking R equal to 0. And so we're just taking the quotient over this subgroup. And so we have this, right? And this is exactly the CQ of U FP. Okay, so this is the first part of the spectral sequence in degree 0, I mean in the page 0. And what is D0, right? So D0 is induced by D, right? So D0 from EPQ0, that is isomorphic to CQ UFP, to the EP Q plus 1 0, that is isomorphic to CQ plus 1 du fp, it will be just given by the d, the big D, it will be minus 1 to the p delta, where delta is the check differential. Okay? So the 0 page of the spectral sequence is just the check complex. Okay? So what is the first page? So since D of Z PQ R plus 1 is contained in Z P plus R plus 1 Q minus R, and it's inside B P plus R Q minus R plus 1 R. Okay, since this is true, we have the following. We have a natural map, a natural projection map. So that takes each CPQ R plus 1 element to the kernel of EPQR dr EP plus R Q minus R plus 1 R, right? This is exactly what this, that this is contained in this means that whenever you take an element here, you look at it inside the EPQR and you apply D to it, it will be 0 in this quotient, right? So it will be in the kernel of this map. Okay, so we have a natural map from here to here, and is an exercise to check that it induces an isomorphism that goes from EPQ R plus 1 equal to this quotient to this other quotient that is, it's the cohomology associated to the R page of the spectral sequence. Okay, and so we can compute the higher order pages of the spectral sequence via the cohomology of the previous pages of the spectral sequence. Okay, so okay, so in particular, the page 1, it will be isomorphic to the cohomology of the complex at the page 0, right? That is exactly the check cohomology groups, right? So it will be isomorphic to this part, to this check cohomology group. Right, and so, and the D1 map again is induced by D, so it will be exactly D, and we'll go to P plus 1 Q1. There is HQX FP plus 1. Okay, and it's induced by the differential D of the complex F. Okay, so here, so at the page 1, we obtained the right part of the equality we would like to have, right? Okay, so right here I will put a remark. Okay, so for every pair PQ and for R bigger than Q plus 1, we have the following equality. So the EPQR part of the spectral sequence, it will be exactly what? So it is CPQR over BPQR. And what is CPQR? CPQR is exactly the space of forms omega in Fp Lp plus Q such that d omega belongs to Fp plus R of Lp plus Q plus 1, right? But we know that R is bigger than Q plus 1, right? So this part of the filtration will be in the superindex bigger than P plus Q plus 1, right? So this group will be 0, right? So for R big enough, we have that the ZBQR part is exactly the kernel of the map D. Right? And again, whenever you compute BPQR, that it is the CP plus 1 Q minus 1 R minus 1 part plus the D of this other group, you will get that this is exactly the kernel of the map D that goes from Fp plus 1 LPQ plus the D of some group that it will correspond exactly to Fp of Lp plus Q intersected with the image of D. Okay, so whenever you compute this for Q big enough, you will have this equality, and it will be independent of the value of R, and this will be exactly the pth part of the filtration of the hypercohomology group over the P plus 1 part of the hypercohomology. Okay, and this is the node that like this, the graded part, the pth graded piece induced by the filtration. Okay, and we will define this as to be the group EPQ infinity. Okay, so we know that eventually, whenever you fix P and Q and you start getting bigger and bigger R, you will eventually stabilize in some EPQ infinity that will correspond exactly to this quotient. Okay, so what we want to check is when does this EPQ1 is isomorphic to the EPQ infinity. This is the question we want to answer. Okay, so a definition. We say that the spectral sequence EPQR dr degenerates at ER if for every k bigger or equal than R, dk is 0. Okay, so in particular, so since we know that we can compute the R+1 page of the spectral sequence as the cohomology of the R page, and we know that all these dr are the zero map, the cohomologies will be exactly the same group, right? So in particular for k bigger or equal than R, we will have that the EPQR k is isomorphic to EPQR, right? And so it will be isomorphic to the EPQ infinity, right? So whenever you have that a spectral sequence degenerates at dr, you will have that from this point it will be exactly the graded part of the hypercohomology associated to the filtration induced by the naive filtration. Okay. So what we want to check is when does the spectral sequence degenerates at E1, right? And we say that the spectral sequence abutes to the hypercohomology and is denoted like this. So EPQR abutes to the hypercohomology. Okay, so whenever you have the spectral sequence degenerates at E1, you will have a non-canonical isomorphism, right, of this type, right? Right, so in particular, in the case where f, for instance, when x is a complex manifold, and you have that f is the Rham complex, what will you get here? So when x is a complex manifold, well, in fact, this is not correct. I mean, this is very. This is not correct. Okay, this is not correct in the case we're just talking about abelian groups. Okay. I don't know. In the case of abelian group, no, it's. I think it's correct. Okay. But well, this isomorphism is not canonical. Okay, it's just the isomorphism of this with the graded, which is each of the direct sum of the graded parts, right? So when X is a complex manifold and F dot is equal to the Rham complex, right? We will get here the hypercohomology group of the Rham complex. But what is this? I mean, so take here. No, what I want to do here is, is the analytic, the Rham complex, right? So you will get here something like this. Right, and this will be so how do we compute this hypercohomology group? So in the analytic context, we will have that this complex will be a resolution of the constant sheaf C over X, and so this will be isomorphic to HK of X with coefficients in C, and this will be the Rham cohomology, right? We will have something like a Hodge decomposition, but it's not canonical in the sense of the Hodge decomposition that we already proved, right? We don't have the symmetry. I mean, we don't have even a canonical way to put this group inside this other group, okay? So, I mean, this is kind of the motivation why we're interested in knowing how to determine when does this spectral sequence degenerates at E1, right? And so now I will give you just a very simple criteria of how to know this. So, well, this is not a standard language. So, well, let F dot be a complex of sheaves over X, and U be a good covering. Respect to F dot. Okay, so we say that an element omega p, that it's in CQ of U FP, is extendable in hypercohomology if there exists some omega p plus j in C q minus j U f p plus j for j equal to 1 up to p, such that the sum of these guys represents an element in hypercohomology. we say that omega p in CQ U FP is R extendable if there exists omega p plus j in C q minus j U FP plus j for j equal 1 up to R minus 1, such that the d of omega p plus all this omega p plus R minus 1 belongs to the part p plus R of the filtration of LP plus Q plus 1. Okay, so what I'm saying is that the omega p is extendable in hypercohomology. So you have to keep this in mind, right? You have here CQ of U FP CQ minus 1 of U FP plus 1 and so on, right? C0 U FP maybe here C, this will be in R minus 1 Q minus R plus 1 of P minus R plus R minus 1 and so on. Okay, so you have here an element omega p here. I'm saying that it is extendable in hypercohomology. Whenever what happens? Whenever you take the d of this, I mean the delta of this element, there exists some other element such that the d of this element is exactly the delta of your element, your original element, right? I mean this will be one extendable, right? Whenever you have this relation. And two extendable will be that you have this element here that satisfies this relation, and also the delta of this, the d of this element will be delta exact. You will be able to produce another element here that satisfy that the d of all these two, this sum of three objects is 0 up to some to the first two parts, right? And that is the idea. I mean, being R extendable is that you can extend it up to the row R, right? And extendable in hypercohomology is that you can extend it to the whole hypercohomology group. Okay? That is just the idea of the definition. So proposition. So the spectral sequence EPQR dr degenerates at ER if and only if every R extendable object omega p in CQ U FP is extendable in hypercohomology. For every P and Q. Okay, so this is what the degeneration of the spectral sequence is saying. So whenever you have something that you can extend up to some point, it will be extendable to the whole hypercohomology. Okay, so the proof is elementary. So So if omega p is R extendable, and we assume that the spectral sequence degenerates at ER, so we know that there exists this omega p plus 1 up to omega p plus R minus 1, such that the D of this thing belongs to the p plus R part of the filtration, right? In other words, we know that this omega p plus R minus 1 belongs to the Z PQ of R. Okay? And so since we are assuming that the spectral sequence degenerates at ER, so since dr is 0, it follows that the D of this thing belongs to B PQR, right? This is exactly Z P plus 1 Q minus 1 R minus 1 plus D of Z no, sorry. It doesn't. It's not PQR. It belongs to B P plus R Q minus R plus 1. Yeah, it's the dr applied to this, and this is P plus R plus 1 Q minus R, and D of P plus 1 Q minus R 1 R minus 1. Right? And so we know that there exists some element here such that this minus D of this object here belongs to this space here, right? So we know that D of some omega p, so there exists this eta p plus 1 plus eta p plus q in f p plus 1 L p plus q, such that the difference, the D of omega p plus 1 minus eta p plus 1 plus up to omega p plus R minus 1 minus eta p plus R minus 1 minus eta p plus R minus eta p plus q. This belongs to Z p plus R plus 1 q minus R minus 1. Okay, so and this means that, in other words, omega p is R plus 1 extendable. Okay, so what we prove is that whenever we have an element that is R extendable, it is R plus 1 extendable. And so iterating this, you will get that omega p is extendable in hypercohomology. Okay, so and conversely, so if you assume that every R extendable object is extendable in hypercohomology, we want to show that the spectral sequence degenerates at ER. And so, well, it is enough to show that dr is equal to 0, right? Since obviously for k bigger than R, every k extendable object is also R extendable, and so it will be extendable in hypercohomology. So how do we prove that the dr is 0? Take any object, omega p to omega p plus q in fp lp plus q. Well, here in the CPQR. Okay. Then we know that d of omega p plus q belongs to fp plus r of lp plus q plus 1. And this is by definition the definition of omega p being r extendable. Right? Omega p is r extendable, and so is extendable in hypercohomology. And this means that we can write this means that there exists some eta p plus 1 up to eta p plus q such that the d of omega p plus eta p plus 1 up to eta p plus q is 0, right? And so the d of eta of omega p plus q is exactly d of omega p plus 1 minus eta p plus 1 plus omega p plus q minus eta p plus q, and this will belong to the fp plus r plus 1 of lp plus q plus 1. Well, it will belong to this, to the d of z p plus 1 q minus 1 r minus 1, right? And this is contained in b p plus r q minus r plus 1 r, right? And so the d of this object will be 0, right? The dr of this object. Okay, so with this, I can give you a criterion. It's a very simple criterion. So proposition the spectral sequence EPQR dr degenerates at E1 if and only if the natural map that goes from the hypercohomology is injective. For every p. Okay, and furthermore, when the complex is gamma cyclic, this is equivalent to the fact that HQ of x fp hat to HQ of fp is surjective for every P and Q. And this is equivalent where Fp hat is by definition the kernel of the D map from Fp to Fp plus 1. Okay, and this is equivalent to this other map HQ Fp, the D map is 0. Okay, so these are the criterions of how to prove that this spectral sequence degenerates at E1. So the proof. So how will we prove that this? Well, I don't know what time is it. I will leave the proof for the next class. Okay. Okay, so I will prove this at the beginning of the next lecture.